everybody. I hope you had a great Easter weekend. Maybe you got to go to grandma's house or something, get together with some family. I mean, all of our family came over our house that's here. Over, my wife fixed a ham, and we just sat around, had a good time. My little grandson turned 2 on Saturday, so that was exciting. That was cool. He's a lot of fun these days to hang around because he's repeating things you're saying, learning new words, all that good stuff. A lot of good stuff there. So that's fun these days. Anyway, how many are we missing here? Fifth period. Oh, we're still missing several. We're missing like 10 students at the moment. Okay, 9. But folks still grabbing some breakfast, I guess, trying to get ready. But we're going to start pretty soon. I was looking in Buzz, and I was trying to look at what I did last year, and I'm not real sure how that went. That's not really in order, I don't think. Maybe it is. Uh, Looking at last year, what I did, I've got 2 lessons scheduled for today, and I'm not sure that's going to work because I'm not sure how long this first lesson is going to take us to go through. So we may end up adjusting that. We'll see as we get into it. And if we have to push one back, we can do that. Not a major problem there. But anyhow, time is running short. We have to start thinking about those things because this is a class that has several seniors, and seniors are going to be done before the rest of us, right? So seniors have, let's see, this week, next week, that week, 1, 2, 4, like 5 weeks. 5 weeks is all left for seniors. So we're getting close to wrapping it up, and then we're just 2 weeks past that for the rest of us. So all that is coming up soon. So just got to pay attention to that as I'm going through this to make sure I know the deadlines and how long everyone's going to be here. So I would say about half the class is seniors in here. About half. Let's see. I guess I could sort that by juniors and seniors. Okay, there's a few more than half seniors, but we've got a big chunk of juniors in here as well. So don't worry, I've got good stuff for us to do after the seniors leave too. We'll look at some things. But anyway, it is 9 o'clock. I want to get started with this. Like I said, I'm not sure how long this first lesson is going to take us, but we will figure that out as we get into this. Algebra 3. Let's go to our grade screen. Should be through with all of that matrix stuff, all the way down through quiz 4. Now, that was last week. So if you're missing any of these matrix assignments, be sure you can go back and get that. If you're missing anything up here, that's way past due. That was February. But the matrix is now finished. So make sure, go to the grade screen, make sure you don't have anything missing there. And if there was one that you did and didn't get posted here, maybe if you were logged in on Khan Academy, it's still there. You can take a screenshot of it. But let's get all of that turned in. Make sure you're 100%. That being said, there's not a whole lot of folks in here that are behind. And the ones that are behind aren't behind that far, just a week or 2 maybe. So again, double check, make sure you got all that. We're scheduled to do quadratic functions and polynomial functions of higher degree. Like I said, that may be flexible. It may have to be flexible because I'm not sure if we're going to get through all that. If we have to bump some of it, rearrange, we will. But we're going to start with quadratic functions. Hopefully we go through this pretty quickly because it's not like it's the first time we've seen quadratic functions. You look at those all the time in algebra. So we're going to go with the quadratic functions lesson right here and see how far we get. Now this is our other curriculum that we look at. Some of these units, this is all on one page, right? We looked at a unit like this earlier in the year. This is from a pre-calculus textbook. Algebra 3 is an Arkansas course that a lot of states don't have. So I built the curriculum from some Algebra 2 and from some pre-calculus and whatever we need to cover the topics that we cover in this class. So the way we do this, as a reminder, when we have this textbook, is we go through the scenic overlook. Scenic overlook. That's right here at the beginning, and this is a nice summary of the entire lesson. And so we'll go through that until we get down to this page. You start seeing all these examples of colors. This is actually the lesson. So this repeats what we look at up here. It just does it in more detail. If you need more explanation of some of the stuff, if it's confusing what we go through, you can go down through the lesson and get more detail and more examples. So we don't go through this in class, but it is here for you to look at if you need it. So we're going to go through and see what it has in the scenic overlook and move on from there. So, oh, wait a minute. Your attention, please. Oh, there's a fire drill. All right, guys, I'm going to be out of the class for about 5 minutes, so we're going to take a break. If you didn't finish your breakfast, here's a good opportunity, and I'll be back in just a few minutes. If you see any fires, be sure and notify somebody. Get that put out before I get back. Okay, made it back. Uh, doesn't look like anything burned down. I guess any firemen come running through the room in a panic or anything. No, no, just a fire drill. All right, let's get back to this. Like I said, this is our scenic overlook, so we're going to go through here, and then we'll take a look. We'll do some examples on paper as usual. Let me sharpen my pencil. And that way we can have some notes to take in addition to what we have here in the lesson. Let's see if I can make that a little bit bigger. Okay, in the next two sections, we're going to look at polynomial functions, and we're going to begin our study with the formal definition of a polynomial function and apply that to a second degree function called a quadratic. Nothing new there. Okay, here's the definition of a polynomial function, just a polynomial. And this textbook is very college level in the vocabulary it uses and the way that it presents things. So we will read this and then we'll break it down into a little more simpler English. So let n be a non-negative integer. Okay, that just means it's 0 or larger, and it's an integer, so it's a counting number. It's not a fraction. And let a sub n to a sub 1, a sub 0 be real zeros where a sub n is not equal to 0. Okay, so the function given by f of x equals a, and a would just be a coefficient, a sub n, x to the n power, and then next is x to the n minus 1 power, all the way down to just a constant. It's called a polynomial function of x that has degree n. So like if this is 4x to the third plus 2x to the second, et cetera, plus 1 at the end. It's just saying that's what a polynomial is. It has an x in it to some degree. Okay, do not let this definition scare you. Each a is the coefficient, and we write the polynomial in descending order with the highest degree first, right? If it's a fifth degree, we're going to start with the x to the fifth as the first term. We classify normal polynomial functions by degree. That is, if it's just a constant, f of x equals 3, that's degree 0 because there are no x terms. If we have a linear function, ax plus b, like 3x plus 1, that's a first degree because x is to the first power. But we're going to study polynomials with the degree of 2, which are called quadratics. Like I say, this is nothing new at all. But let a, b, and c be real numbers, and the only requirement is a cannot be 0 because that is the coefficient of the x squared term. If that was 0, we would not have an x squared. It would not be a quadratic function. So the function is f of x equals a to the x squared plus bx plus c. Now, b or c could be 0. We could just have like x squared or 7x squared or negative 2x squared. But we have to have the x squared term for it to be a quadratic function. And the graph of a quadratic function is a U-shaped curve called a parabola. We know that. All parabolas are symmetric around a line called the axis of symmetry. And we know the axis of symmetry runs through the vertex right down the middle of the parabola. The point on the parabola where the axis intersects the parabola is called the vertex, which would be either the highest or lowest point in an up and down parabola. A parabola opens upwards if the leading coefficient is positive, and it opens downward if the leading coefficient is negative. So if it's 2x squared, it opens upwards. If it's negative 2x squared, it opens downward. That's what that's saying. The simplest quadratic function is f of x equals ax squared. And a could be 1. Maybe it's just x squared. This parabola would have a vertex of 0, 0, and the axis is the y-axis. That is the axis of symmetry. The parabola opens upward when a is greater than 0 and down when a is less than 0. So look at the text to see the shape of a basic parabola. Well, that's way down in here. So this is the shape of a basic parabola, either up or down. All right. Test your skills. Do I have this? I don't have the answer key on here. But this is a graph. Graph each of the following functions and see how it differs from ax squared. So we're going to open up Desmos just so we have that graphing capability. And it wants us to compare it to y equals x squared. So this is the basic, most simple quadratic graph. So let's see how 1/4 x squared compares to just the basic graph. Y equals 1/4 x squared. Okay, the blue graph is the graph of 1/4 x squared. So the coefficient of 1/4 makes the graph, the parabola, be wider than normal, right? The red is the normal parabola, the blue one is wider. And why is that wider? Why would 1/4 do that? Well, let's look at like a point on the graph. Like if we look at the original graph, we have the point 2, 4 right here. When x is 2, y is 4. But if we take that to 1/4, when x is 2, 1/4 of 4 is only going to be 1. So that's why it gets wider, is because each of these points is only 1/4 the height that it used to be. This used to be way up at 4, and now it's only at 1 because it's only 1/4 this height. When it gets to 2, that's when normally the graph would be way up at 8 up here. See, we have the point where it's 8, which is only 2 now. It's 1/4 the height. So that is the graph 1/4 of x. If we look at 4 instead of 1/4, let's just make that a coefficient of 4. Well, now instead of being wider, it's skinnier. And it's skinnier. This should make sense as well. When the graph was at 1, now it's 4 times taller. Now it's up here at 1/4 instead of 1/1. So it's growing 4 times faster. Before it was growing 1/4 times as much. So it was just wider. It was taking longer to go up. Now it's going up faster. Let's look at 4x squared plus 4. So what happens to this when we put a plus 4 on the end? Okay, when we put a plus 4 on the end of our graph, it simply raises up the vertex. The entire graph is lifted up a distance of 4 units. Instead of being at 0, 0, where it was down here for the vertex, now it's gone up to 0, 4. It's still a skinnier graph because we have the coefficient in front of the x squared of 4, but we have raised the values 4 points. Let's see, they want us to look at negative 4x squared. So let's take the plus 4 back off. go to negative 4x squared. If we put a negative in front of it, it simply flips it upside down. Now, instead of all the values going up, they're going down, because when it was a positive 4, now it's a negative 4, because we just multiplied it by a negative instead of a positive. So it's just like the 4x squared, it's just reversed upside down. Let's look at just x squared minus 4. Okay, let's take off the negative 4. We're back to just x squared. And if we put a minus 4 at the end, it takes the original graph. This is the same graph as the red one. It's just lowered by 4 units on our graph. I'm going to take off these minor grid lines and make these just ones. There. Okay, I like that better. 1, 2, 3, 4. You see this has gone down 4 from where it originally was up here at 0, 0. 0, 0, 0, 4. Negative 4. Down 4 units. Let's see. 1/4 x squared plus 4. Let's do a lot of stuff here. All right. We're going to go back to the original graph. We're going to put the 1/4 in front of it. Remember, that made it wider. And then they want us to put a plus 4. Add to the end plus 4. And it just takes the graph and raises it up 4 places. Instead of being down here at 0, 0, it's now up here at 0, 4. So that's just looking at how the graphs of quadratics change as we add coefficients that are larger than 1 or smaller than 1, and how we add numbers after the x squared. So let's talk about the vertex form of a quadratic function, and I'm going to put this in our notes. Okay, starting our notes for today. Get that to focus in nicely. The vertex form of a quadratic function looks like this. F of x equals a. That'd be the coefficient. Remember, when it was 1/4, that made it wider. When it was 4, it made it skinnier. So that's the coefficient. X minus h squared plus k. This is the vertex form, because from this, we know the vertex is at h comma k. Now notice this is h minus h. So if the vertex is a negative h value, this is going to be x plus, because x minus a negative h would make this look like an x plus, because when you subtract a negative, that's adding. So this tells us, the vertex form tells us right here in the equation what the vertex of that quadratic parabola will look like. So that's why we like the vertex form. It can save us a lot of work if we're looking to see how to graph our parabola. It can tell us exactly where the vertex is. HK, the axis, the vertical line. Oh yeah, let's see, the axis of symmetry. So here's where I want your focus to be. Axis of symmetry. Let's put that on there. Is x equals h, whatever that h is, because remember the line of symmetry always goes right through the vertex. So it will go through right where the h is in the vertex hk coordinate. X equals h. Okay, what else do we talk about? Oh, and the question is how to get a quadratic equation into the vertex form. We can do that by a method called completing the square. So let's walk through that. 5x squared. I'm going to write this one down. And I'll need on my answer. Okay, so completing the square. This is generally the easiest way to do this. Anything, I set it equal to 0. They do it a little different in their example. I like to move the constant to the other side. 5x squared plus 10x equals -6. I've moved it to the other side. Then we're going to factor out a greatest common factor. Well, actually, we want to leave the x in there because we need the quadratic, but we'll just factor out the 5. Because I just want an x squared. I'm going to factor out whatever I can here, plus 2x, and I'm going to leave some space. So inside here, I need to make this a perfect square trinomial. If you don't remember what that looks like, I'm looking for a trinomial that I can just do x plus something squared to equal this. So what would I need to add on here? The way you do that is you take the middle term, the 2x, the 2, let's see, we'll take it right here. Where do I want to do this? I want to do this right over here. I'll take the 2 and I divide it by 2. Well, 2 divided by 2 is 1. And then I take that number and I square it, which is also 1, to add right here. So this is, since this is a 1 inside here, that's the number I use right there. The squared number is the one I add up here. But since I've added to this side, I have to add this side to make it equal, right? Let me show you this. If I did this, does that work? That is actually wrong because I did not add 1 over here. Like, what do you mean you didn't add 1 over here, Mr. Brock? I just saw you do it. You put a plus 1. Well, I did put a plus 1 inside the parentheses, but everything inside the parentheses is being multiplied by 5. So if I add 1 inside the parentheses, I've added 5 to this side. I have to add 5 to that side in order to still be equal to each other. So negative 6 plus 5 is now negative 1. To get this back in vertex form, we're really close. We just got to add the 1 back over here. So this ends up 5x plus 1 squared plus 1. This is vertex form. So now I know for this quadratic equation, the vertex is at negative 1, 1. Remember, this is a plus 1, so h must be a negative. And we're going to graph this to see if we're right. This is the vertex form of that. If we're correct, this graph will have a vertex of negative 1, 1. And since it has a 5 out front, it's going to be real skinny. So let's go to Desmos. And let's graph that. Comparing it, we'll leave the original one on there. Y equals 5x squared. I want to put our negative 1, 1 on there. Just see if we're right. Negative 1, comma 1. All right, there's our point that we think is going to be the vertex right over here. 5x squared plus 10x plus 6. Look, that is the vertex. Our vertex form must be correct because that is the vertex. We said it would be at negative 1, 1. Here it is, 5x squared plus 10x plus 6. If we put it in the vertex form, it should be the exact same graph. When we said 5x plus 1 squared plus 1, it is. It's the exact same graph. Say both graphs are the same thing. And it should be. If it's just the vertex form of the same equation, it should produce the same graph. So that shows that this is the vertex form of this equation because they produce the exact same graph. So we can always get to the vertex form if we need to. If we just have the standard form, we can change the vertex form by completing the square and getting that vertex and the axis of symmetry at x equals negative 1. And they walk through this as well and show that negative 1, 1 is the vertex and all that kind of stuff. Okay, it says put the following into standard quadratic form. Oh, standard quadratic function form. Find the vertex point and the axis. Well, these are already in standard quadratic function form. It's ax squared plus bx plus c. But to find the vertex point and axis, I think they want us to complete the square. Either that or we can graph it. Oh, they want graph it is right there, thirds. Let's just do the first one. We won't do both of these in the interest of time. You can certainly do both at your own leisure there. I'm going to move the 7 because I think it just works a little better to do it this way. I'm going to factor out the 3 x squared plus 4x, leave some space, equals -7. So you see we've moved the 7 to the other side, and we factored the 3 out of what's left over here. So I can just have an x squared term. Okay, there's that middle term. 4 divided by 2 is 2. So that's what's going to be here, x plus 2. And that's a positive, so this is a positive. Don't know what's going to have there. And then when I square this, I get 4. So I'm adding 4. But if I'm adding 4 inside the parentheses, I'm actually adding 12 because it's being multiplied by 3. So I have to add 12 over here. So that makes this a plus 5. So subtract the 5 back. 3x plus 2 squared minus 5 equals 0. So our vertex, this is a positive, so that must be -2, -5. What else do they want us to know? They want us to find the vertex point and the axis of symmetry. X equals -2. That would be the axis of symmetry. All right, let's graph this and see if we're right, because that's what they have us do on number 3 is graph these functions to show that. Check your graphical calculator. We're using our online calculator. They do have a check your answers in this one. So hopefully I've put that in there. All right, let's go back and graph. I'm going to take off all this. I'm going to put the point that we said. We believe it's at -2, -5, and that our axis of symmetry is x equals -2. Okay, so there's where we believe the vertex to be and the axis of symmetry. Let's put in our equation to see if we're right. It was 3x squared. I'm putting in the original equation because that's what I'm checking. Plus 7. Hey, perfect. Look at there. So I believe we're correct because that is the correct vertex that we ended up with. I'll go ahead and check with our simplified vertex form. It was -5. Yep, same equation. Same equation. We ended up with the exact same thing. We do have a check your answers. You can click on there. And so if you do the other example, yep, it does load. So, but there it is. Vertex -2, -5, axis of symmetry. So I'll leave this other example you can do. You can check your answers. And since I have that on there, I'll leave that. Solving a quadratic equation set equal to 0. From the Algebra 2 class, there's several ways to solve a quadratic equation set equal to 0. This is our standard form of a quadratic equation, ax squared plus bx plus c. We're used to that. Provided that it's factorable, we can solve each factor and by setting that equal to 0. For example, if we have x squared plus 3x plus 2 equals 0, it factors to x plus 2x plus 1. So we can set each factor equal to 0. X plus 2 equals 0. We'd have a solution of x equals -2. X plus 1 equals 0. X minus 1. And this is always important to remember, if the quadratic is not factorable, or if it's difficult to find, or if you just want to, you can use the quadratic formula, which is right here. Here's the quadratic formula. So I'll put that in our notes as well, just so we have it. Because remember, we can use our notes on the tests or anything. Assignments, tests, the semester final. So I just want to make sure somewhere in my notes, I've got the quadratic formula. And it is x equals -b plus or minus the square root of b squared minus 4ac all over 2 times a. And where do these a's, b's, and c's come from? A standard quadratic equation in the form ax squared plus bx plus C. That's where the A's, the B's, and the C's come from. They are the coefficients. They are the coefficients. So we have that in our notes, the quadratic formula. And they have it on that page of our lesson as well. I just want to have it in the notes so I have it all in one place when I go to take the tests. Make it easier on myself. There's negative b plus or minus b squared minus 4ac over 2a. And it's ax squared plus bx plus c. So they do an example where they solve 2x squared minus 5x plus 1 equals 0. Guess we can do that. Yeah, this is the last example because then it gets into the lesson again. So let's go ahead and do that with our quadratic formula, just so we have that. We're going to use the quadratic formula to solve this because it doesn't look factorable, or it looks like it'd be hard to factor if it is factorable. So A is 2, B is negative 5. Let's write over here. A is 2, B is negative 5. Don't forget, if it's a minus, you need that negative with your coefficient. So x equals negative b, negative 5. That's going to be a positive 5, plus or minus negative 5 squared, because it's b squared, minus 4 times a is 2, c is 1. And all over that is 2a, 2 times 2 in this case. Now it's just a matter of simplifying this as much as we can. Negative 5 is a positive 5, plus or minus. I'll go ahead and put this. Negative 5 squared is a positive 25 because it's negative 5 times negative 5. Minus 4 times 2 times 1. Well, 4 times 2 is 8. 8 times 1. It's all over 4. So this simplifies to 5 plus or minus the square root of 17 over 4. Square root of 17 is not an integer. It's 4 point something. So we leave the answer like this, which there are two answers. Remember, quadratics is 2x's, and there are two answers right here. So if we want to break them apart, one is 5 plus the square root of 17 divided by 4. And the other one is 5 minus the square root of 17 over 4. If you're going to graph those, that's where it crosses the y-axis, right? That's the solutions. That is the actual values of the solution. If we wanted to graph those, we would take our calculator to figure out where that crosses the x-axis at. Let's see. 5 plus the square root of 17 divided by 4. So this equals about 2.28 as a decimal. The other one would be 5 minus the square root of 17 divided by 4, or about 0.2, well, we'll round it to 2 decimals since we did the other. 2.28 and about 0.22, just a little bit past 0. So let's check to see if we're right. 2x squared, this is again solving for the zeros. 2x squared minus 5x plus 1. Oh, I did something weird with the x. Oh, I got a caps lock on. That's a problem. Okay, there it is. So we said one was at 2.28 and the other's at 0.22. There they are. Those are the solutions, because when we graph it, the solutions are where they cross the x-axis. It may have imaginary solutions, remember. Quadratics could have imaginary solutions, because if this was a +3 instead, or no, +4, there's no real solutions. They're all imaginary. But since it's +1, we were able to find the actual solutions. And we would leave it like that. We would not do it as a decimal unless we were graphing it. So, all right, and this goes through the same stuff. It just gives some more examples. So you can go through here if you need to and look at, there's the vertex form again, which we've already looked at, axis of symmetry, and have more of that. Let's look at the assignment that goes with this first lesson. Find the vertex of the graph of this function, and it's in vertex form. So we don't need to graph it at all. We can just look at this for h and k and select that. Find the vertex of this one. This one's in standard form. So if you complete the square, you can put it in vertex form. Or you can graph it. Find the axis of symmetry. Again, that would be the x value of the vertex. This is not in vertex form, but you could convert it or graph it. Write this one in vertex form. Say this one you may need to go ahead and complete the square. Convert that to the vertex form. And oh, we have one that we have to actually type our answers. Now remember, use this insert equation button if you have to type this, because it has like this equation here. I don't know if we use that equation, but if you're putting that in there and you're doing, something squared, we want it to look like this, not like this. If we use the insert equation, look, -16t squared plus 704t. Says the projectile is thrown upward, so its distance above the ground is given by this function. At how many seconds does the projectile take to reach its maximum height? That would be the vertex. The x of the vertex would be the seconds. The y is the height. So if you find the vertex of this equation, h of t equals this, find the vertex of that quadratic equation. You can change that to x's if you want. If you don't like working with t squareds and t, change it to x's, but it's still whatever your variable equals is the solution. So, all right, let's save an X at that. Let's look at our second lesson. So 4 multiple choice and 1 fill in the blank. Okay, our scenic look, polynomial functions of higher degree. So let's look at something larger than a quadratic. In general features of polynomials, first of all, they're continuous. There's no break in the graph. Like if we graph this and we make it x to the 7th, and this is 5x to the 4th, and this is 1x, let's make that one squared, -2. It's continuous. You could draw that without picking up your pencil. If I gave you a sheet of graph paper and said, draw this, it's continuous. There's no breaks in it. It doesn't have asymptotes. There's no holes in this graph. Polynomials are generally continuous. That's how polynomial works. They are continuous. There's no sharp or pointed turns. The graph is smooth and rounded. In this one, even though I made a weird one with the 7th degree and 4th degree and squared and all that, it's still, there's no sharp turns. I mean, that's pretty steep, but it's still rounded. The more you zoom in, you'll see it's still a rounded corner. It doesn't come to a point. It is a smooth corner, even though it's a pretty sharp turn. See, we can see that. So that is the basic features of polynomial graphs: x to the 3rd, x to the 4th, x to the 5th, x to the 20th, whatever it is. And polynomials with the easiest to see form are those called monomials, like it could just be an x, y equals x, or -2x, or whatever it is. That's the simplest polynomial. It's a 1st degree. But it could be 2nd degree and 3rd degree and 4th degree and whatever. Let's see. If n is an even integer, the graph is U-shaped. If it's an odd, it'll be S-shaped. Okay, so that's a good thing to talk about. If, let's just take away all this extra stuff. I'll take away the 2 even. If the graph is an even number, it's raised to the second power, it's shaped like a U, right? If it's raised to the fourth power, it's shaped like a U. The sixth power, oh, I hit five. Sixth power, eighth power, 12th power. Now the U gets steeper and steeper, but it's all a U if this is an even number. If it's an odd number, 3, it's kind of S shaped. 5, 7, 9, 11, 20, 21, 23. There's 23. It gets more steep very quickly, but if this is an odd number, it's more like an S shape where one side goes down, the other side goes up, compared to an even number where it's more like a U. So that is the point it's making right there. Graph the following and observe the changes in the graph as the function changes. So let's talk about transformations again. We're going to start with x to the third. That's this one right here. X to the third. What happens if we make negative x to the third? Okay, let's compare that. Y equals negative x to the third. Okay, this is x to the third. This is negative x to the third. X to the third, negative x. It just flips it around. Put a negative, everything that went up over here is now going down. And what went down over here is going up. So it just basically flips it upside down. All right, let's look at x to the fourth. Turn this one off. X to the fourth looks like that. Kind of looks like a parabola, except it's a little steeper. It goes up faster compared to x to the fourth plus 1. So over here, let's do x to the fourth plus 1. Ah, look there. It's the blue graph. It looks exactly like the black graph. It's just raised up. The vertex is 1 higher. That middle point is 1 higher. And let's set x plus 1 to the fourth. Let's compare this to x plus 1 to, oh, I got to delete all the rest of that, to the fourth degree. There is x plus 1. This is kind of like the vertex form of a quadratic, where you got that x minus a number in there, x minus h, and the h should be negative 1, which is the vertex. It went from 0 to negative 1, the h value, because we put it inside the parentheses with the x. So x minus a negative 1, it does tell us where that vertex point is. If this was a minus, it'd move the other direction. Now it's on the right side. And finally, 1 minus x to the fourth. Oh, that'll be different. So let's make this just x to the fourth. There's x to the fourth, and let's do 1 minus that. Well, that's interesting. Not only did it flip upside down, it moved up 1. It moved up 1 because there is a plus 1 up here. So the plus 1 raises it up, and the negative coefficient in front of the x to the fourth reverses it where it goes down instead of up. So there's a plus 1 out there that makes this change and go up. All the values go up 1. All right. Oh, the binomial theorem and Pascal's triangle. Oh, yeah, this is pretty cool. So, let me see. See if I can draw this. Oh, I have a link to it right here. Well, it's not. Oh, it is a link. The binomial theorem and Pascal's triangle. Okay, the binomial theorem. Theorems are real mathy, right? Using the binomial theorem, the coefficients for a binomial raised to any power can be found with these combinations. N factorial times over divided by r factorial divided by n minus r factorial. And you're like, oh my gosh, what in the world is that? Let me give you a look at what factorial means, because you may see that sometimes. Sometimes on some memes, they like to do that to trick people that don't know math. 5 factorial. An exclamation point is factorial in math. And what that means is 5 factorial equals 1 times 2 times 3 times 4 times 5, right? Which we could do it. 5 times 4 is 20, times 3 is 60, and 60 times 2 times 1. So 5 factorial is 120 because it's 1 times 2 times 3 times 4 times 5. And you'll even see that on calculators. A lot of factorials, there it is, in factorial. There's a lot of calculators that have a factorial button. If we hit 5 factorial, see, it's 120. When I was a kid and you had a calculator, you test it to see like a bigger number, 70 factorial. How fast could it do that? Computers do it pretty fast now. 1.19, that's just 70 factorial. If we did 552 factorial, instant. It used to be a calculator would sit there and think and think and think and think. And sometimes if it was too big a number, it would just come back with an error. But it's a really huge number. But that's what factorial is. So when we see in this example, n factorial divided by r factorial by n minus r factorial, we're talking about some numbers that can get big really fast. So Pascal's triangle. Okay, let's look. Let me see if I can draw out Pascal's triangle just a little bit so we can talk about it. I got the first 4 lines there on the screen, but let's look at what this is. 1, 1, 1, 1, 2, 1, 1. That'd be 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, and 1. It's like, what in the world are you doing, Mr. Brock? This is Pascal's triangle. And what this is telling you is the coefficients that if we had, this is a plus b to the 0 power, a plus b to the first power, a plus b to the second power. This line is a plus b to the fourth power, oh, third power. I'm sorry, third power. And you're like, what do you mean this is a plus b to the third power? This is the coefficients. Let me do this. I'm going to do one more and then we'll look at this. A plus b to the fourth. Pascal figured out a lot of stuff in math. So what he figured out is with this triangle, and the way you get this is 1, 1, 1, and then the ones go all the way down this way. The other ones go down this way. To get like this number, you add the 2 above it. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And you keep going down to where, 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6. And you can just go on forever. And what that means is if I have this, if I have a plus b to the fourth power multiplied by itself 4 times, that means I'm going to end up with an equation that has a to the fourth with no b, plus I'll have an a to the third b, plus I'll have an a to the squared b squared, and I'll have an a b to the third, and at the end I'll have a b to the fourth. When you multiply a plus b to the fourth power, and that's multiplying a plus b times a plus b times a plus b times a plus b. And what Pascal's triangle tells you is the coefficients. This will be a 1, this will be a 4, this will be a 6, and this will be a 4. Put it over here. That'll be a 4. The coefficients will be 1, 4, 6, 4, and 1. And a plus b can be any numbers. It could be x plus 2 to the fourth power. So this would be x squared plus b is 2, so it'd be 4 times 2, 8a to the third plus 6 times, well, the 6 would change too because this has a b squared. So this has 2 squared, 4 times 6. So this would be a 24. 24a squared. And then 4 times b to the third, 2. 2 times 2 times 2 is 8. So this would be a 32a plus, and then just be b to the fourth. 2 times 2 times 2 times 2. So x plus 2 to the fourth power is x squared plus 8a third plus 24a squared plus 32a plus 16. Wow, boy, that was a lot shorter than taking x plus 2 and multiplying it times x plus 2, x plus 2, x plus 2. If you multiply all that together, you'll end up with this because Pascal figured out that there's certain coefficients that always play in there. Then you just have to take the math. B is 2, so you have to multiply it by 2. 2 squared times 6. 2 to the third times 4. Pascal's triangle. Pascal, I think he was a lazy man, so he figured out shortcuts for everything. And I'm all good with that. Look at the coefficients, a plus b to the 0 plus a plus b to the third. Here's the fifth row, 1, 4, 6, 6, 4. And they're showing right here what I was doing. A plus b to the fourth power is 1 times a to the fourth b to the 0 power, which is just 1. So all you end up with is an a to the fourth at the beginning. A to the third, a to the second, a to the first, and a to the 0. Meanwhile, the b is growing. B to the 0, b squared, b to the third, b to the fourth. So it simplifies to exactly that, which is what I had written right here. The 4ab third right there. So then they used x to the negative 3 as an example. I did x plus 2, but x to the negative 3. So using this exact same pattern, x to the fourth equals 4x to the third times negative 3 to the first power. 6x squared, negative 3 squared. 4x to the first, that's this 1 and the 6 and the 4. And so when you square the negative 3 over here, you square the negative 3, you get 9, multiply it by 6. You get 54, you get negative 108, you get 81. Because you have to take that negative 3 to the third power, negative 3 to the fourth power, and use that in your math. Much faster than multiplying those 4 binomials together by hand. You can use this pattern. If you have, this only works when you have something like being squared or to the third power, fourth, and it's a binomial. This works for binomials. This is using the binomial theorem and Pascal's triangle. So it gives you a couple examples. Take x minus 4 to the fifth power. See if you can do that. 2x plus 3 to the third power. Here, we'll try one of those. Let's do the 2x plus 3. That looks interesting. So this says, if this is a and this is b, the third power is this row, 1, 3, 3, 1. So we're going to have 2x third, second, first, 0 to the third power. Plus 3 to the 0 power, which is just 1. So we don't put the b. Yeah, this is really b to the 0 power. And out here, if I write this correctly, this is a plus a to the 0 power because it goes a to the fourth, a to the third, a to the second, a to the first, and a to the 0. But a to the 0 is just 1. Anything to the 0 power is 1. That's why I didn't write it the first time. B to the 0 power is just 1. So this is just a to the fourth. This is a to the third for us. Third, second, first, and 0. So this will be 3 is our coefficient according to Pascal's triangle times a is 2x, and this time it's squared. It was to the third power. This time it's squared. And then b. There's b. So now coefficient of 3 again. 2x to the first power. 3 to the third squared. So this is 3 to the 0 power, 3 to the first power, 3 squared. And finally, at the end, we just have 3 to the third. Now we simplified it. We used Pascal's triangle, coefficient of 1, 3, 3, 1. So there's a 1 out here and there's a 1 here, but that doesn't change anything, right? So 2x to the third, 2x times 2x times 2x, 2 times 2 times 2. This should be 8x to the third. 3 times 3 is 9 plus 9 times 2x squared. 2x times 2x is times 4x squared. So that's going to simplify again. 8x third plus 9 times 4, 36x squared. Here we have 3 squared, which is 9, times 3 is 27, and just 2x to the first power. So 2 times 27, 54x. And then 3 to the third power, 3 times 3 times 3. So this is what this equals. Let's check our work. 8, 36, 54, 27. Here it is at the bottom. 8, 36, 54, 27. Yeah, that's it. 8x to the third. We see it right down here. We use this is all the work for doing that one. Oh, that's doing 2 different ways with the binomial theorem, which is different, and we use Pascal's triangle using the 4th row Pascal's triangle. Let's see. We need to look at the binomial theorem because we didn't really. A plus B, A plus B plus. Oh, it's using the patterns of that for the coefficients. They do work together. The binomial theorem. Okay. The leading coefficient test. In the previous test your skills exercise, notice that as the value of x moves to the left or right, the graph will at some point begin to rise or fall without bond, which means it goes to infinity. You know, there's no limit. The rising or falling of a graph is determined by 2 rules. Whether the degree is odd or even, right, which we saw that, odd or even, it goes like if it's even, both go to infinity, you know, without limit, without bound. If it's odd, one end will rise and the other will fall, right? And the leading coefficient tells whether it goes up or down on which end. So if the leading coefficient is positive, the graph falls to the left and rises to the right on an odd degree. But if the leading coefficient is negative, it goes the opposite. So we can get a visual image of how the graph will look by paying attention to whether it's odd or even and what is the leading coefficient. Use the degree and the leading coefficient to determine left and right sides of the graph. So for this, here, I'll write that down. If we just look at this graph, this equation, x to the 5th plus 5x plus 2, we only have to pay attention to the first term. The first term is the boss. It determines what the graph looks like for the most part. The ends, 5th degree, that means one end is up and one is down. This is a positive 1. So our graph is going to look something like that. Now in the middle, I mean, it could do something like that in the middle. That's what these other things determine. But we know the ends are definitely going to be pointing up on the right and pointing down the bottom. That's guaranteed because this is a positive coefficient, positive 1, and this is an odd. So we know the graph is going to go up on the right and down the left. So let's look and see if we're right. Delete that. X to the 5th was that minus That's plus 5x plus 2. Plus 5x plus 2. Whew. It just barely curves. It doesn't curve very much, but it does go up on the right and down the left. That 5x just barely curve. How about this one? This is almost the exact same graphs, just all negatives. Negative 5x. So that's going to be just the opposite. If it's negative, let's change all these to negatives. Minus. Notice that didn't change a whole lot until I do this. Now it's just upside down. Up on the left, down on the right. Let's see. Let's write the next one down. 16x to the fourth minus 2x plus 7. A graph of 16x to the fourth. Again, this is a positive. So it's going to go up. So this end's going to go up and this end's going to go up. And in the middle, we don't know exactly what it'll do, but we do know the ends. Both are going up because this is even and this is positive. If this was negative, it'd be pointing down. But it's not. It's positive. It's up. If this was fifth degree, like the next problem, I think, is like x to the fifth, like 16x to the fifth. If this is a positive, it'll go up on this end and down this end and whatever in between. 16x to the fourth. 16x to the fourth minus 2x plus 7. Yep, it goes up on both ends. It's really, really steep because that's a 16 out front, so it goes up really fast. But both ends point up, and that's what we're really checking here. Do both ends point up or not? Fifth points down on the left, up on the right. 1/2 x to the sixth. X to the sixth means it points up on both sides because this is positive. This is a negative coefficient, and that is the sixth as well, so they're down. When we check our answers on that, it'll show you the graphs of each. Oh, it just tells you the graphs of each. Down left, up right, up left, down right. Up and up, down and up, down and down. Those last two were 16x to the sixth. Up and up or down and down if it was negative. No, 1/2 x to the sixth. Zeros, we know for a function, they're at most in the real zeros and at most n minus 1 relative extrema, which means peaks or valleys. So again, we're trying to figure out how a graph works. So let's talk about the fundamental theorem of algebra. Fundamental theorem of algebra, which we've looked at this back in the fall, I believe, but let's look at that again. 3x to the seventh minus 2x to the sixth plus 4x third minus x plus 2. How many zeros does this equation have? If we graph it, what's the most possible times it could cross the x-axis? All right. How many times could it touch the x-axis? When it touches the x-axis, that's a 0. Some zeros could be imaginary, right? So we might not see all of them, but we're guaranteed we'll not see more than what the zeros are. And remember, the zeros are determined by, let's see, this is x to the third, x to the sixth. Oh, there's a seventh. Whatever the largest exponent. At most, this can only touch it 1, 2, 3, 4, 5, 6, 7 times. It could not touch more than 7 times. It might only touch once. Maybe the other zeros are imaginary, right? But the zeros are determined by the largest exponent. So for this, x equals a could be a 0, x minus a this way could be a 0 because it'd be equal to 0, right? Let's see, what else do they talk about in here? It's a solution. Oh, this is a factor, right? X equals a is a solution or a 0 x minus a is a factor. If that's a 0, then x minus a is a factor of that equation, right? Whatever a is. If x equals 2 or whatever, right? And a factor be x minus 2. And oh yeah, and so then like a comma 0 would be a point on the graph. It's a 0 because we'd see it cross the x-axis at that point. If x equals a is a solution, like if x equals 3, then at 3, 0, we would expect to see it crossing the x-axis. And x minus 3 would be a factor of that equation, whatever, however that works out. For example, for this equation, it factors to 2x to the third, x minus 2, x minus 1. The solutions would be x equals 0, because for this equation, x equals 0, x equals 2, and x equals 1. And so the x-intercepts, if these are the solutions, it would cross 0, 0, 2, 0, and 1, 0 based on these 0, 2, and 1 that are there. Okay, what else we got here? We got a couple things. All right. Find the real zeros of the following. Use your calculator to graph the function and check it by looking at the x-intercepts. So let's take the first one. Yeah, use your calculator to graph that. So we're going to use Desmos. If we were looking at this first equation, x to the third plus 2x squared minus 4x minus 8. What are the zeros of this equation? 2 and negative 2 are both zeros for this equation. All right, so when we check that, I'll close that one. Close that one. Okay. For A, when we graphed A, let's have A and B both on here. Yeah, plus or minus 2. It's really small. Can't really, I guess I could blow that up some. When we graphed that, we saw that there is a 0 at negative 2 and a 0 at 2. So x equals plus or minus 2 is which is the same as 2 and negative 2. By graphing it, we saw the zeros. That means there are 3 zeros. That means it also has an imaginary 0. Since that's x to the third, there's also plus an imaginary. We don't know what that one is because it doesn't show up on a graph when it's imaginary. And then we could do the same thing that, and they said real zeros only. Negative x squared plus 2. Negative x squared plus 2. So it's the point 1.41. That's the square root of 2 and the negative square root of 2. 1.41421. Which says, yes, plus or minus the square root of 2. Let's look at the intermediate value theorem. Again, fancy math vocabulary words. So it says, okay, let A and B be real numbers where A is the smaller one. A is less than that. If f is a function so that the function where A is and the function where B is not the same, then between A and B, f has every value between f, A, and b. It's like, wow, what is that? That is saying a lot. It's actually very simple what it's saying. It's saying if we have a function where if f of a, and let's say a is -1 and b is 3, right? So a is this value, 1, 2, b is this value. And it says f of a, which whatever that means, whatever the y is at a and b, these are not the same. So let's say this is up here at 3, it's down here. And let's say whatever the function does in between there, right? Because we don't know what the function is. It does something in between there and there. What they're saying is if a is a number that's smaller than b, which 1 is less than 3, and these values are the same, that all of this exists. There exist values for the function in between there. That's all that's really saying. The interval a to b, f takes on every value between fa and fb. It's like, it means somewhere, if this is 2, right, this is the point -1, 2, and this is the point, we'll say this is 2, -1, all right? We'll say this is 2, -1. If the point 1, 2 exists and the point 2, -1 exists, that means somewhere this function has every value between 2 and -1. Everywhere, somewhere in between here, between 2 and -1, you can find this function somewhere. Yeah, right here it's 1.5. Right here it's 1. Here it's 0. Here it's just saying all these values have to exist if these 2 points exist. Because you can't get from there to there without crossing all these other values. You can't get from 2 to -1 without 1, 1/2, 2/3, -1/2. All those values have to exist somewhere in there. And maybe it's just a straight line. Maybe they exist perfectly right there. But it's just saying they have to exist somewhere. If this exists and this exists, all the values between there have to exist. It says the theorem is saying that if a f of a and b f of b are 2 points on the graph, then every value of their y values exist in between there. So it says put -2, 1, and 3, -4. Let's see. -2, 1. Oh, wait, that wasn't it. And 3, -4. If you have those 2 points, there has to be somewhere a value for this function at 0 and 1, whatever. Somewhere there are points in between 1 up here and -4 for every point in between there. It exists somewhere. Whether you connect it with a straight line, a quadratic, a cubic, or some other curved function, you don't lift your finger off the paper. So somewhere in between there, there's a value for every y between 1 and -4. However we want to connect these. If we take here, we say we're going to graph go like this, somewhere it exists. If we did it straight, if we had a graph that went, woo, it doesn't matter. Somewhere in between those 2 points, there's a value of y on that function. So that just tells you that if we're looking for a value of this function, we know it exists if it's between 2 points that we know exist. We know somewhere we can find a value between those. That's the intermediate value theorem. Because if this point and this void exists for this function, all the points in between exist as well. Use the intermediate value theorem to show that this has a 0 somewhere between -1 and 0. Well, if you solve this, the zeros are in between. Oh, it has the point -1, 0. Somewhere in between there has to be a 0 because one of them's positive, one's negative. That's what I'll tell you, that somewhere this has a 0 between this value and this value guaranteed, because somehow it has to cross, I can't get to the other point without somewhere I have to cross the x-axis, which that creates a 0 right there. So if I have a value that's above the x-axis and the value is below the x-axis, I know somewhere I've got a 0 in between there. It has to be. Somewhere I have to cross that axis. The extreme value theorem. And let's see, is this and the identify. Okay, that's the end of it right here. So tell you what I'm going to do, because we're absorbing a lot of information today with this. I'm going to stop this lesson right here this week, and we'll pick up at this point. So if you want to do this lesson, I haven't looked at the assignment yet. If you want to do the assignment and think you can get it all done, I don't know if there's any questions about the last little piece of this or not. You can do it this week, but I'm going to really delay it till next week till it's due. So the 8.02, I'm going to leave it in Google Classroom saying it's due this week. I'll probably leave it in Buzz saying it's due this week, but it's not due this week because we didn't finish the lesson. We got 10 minutes left and our brains are pretty mushy by this point. And I want to make sure that I explain this well, the extreme value theorem and the step 1, step 2 of how to do all of this. So we're going to stop there. Like I say, 8.01 is due this week. 8.02 is optional if you think you can get it done without the last of this lesson. But don't worry about it if you don't get 8.02. So we'll finish that up next week and look at next week's lesson as well. We just have one lesson next week, so we'll have time to finish this up. So, all right, guys, I'll give you the last few minutes of class to, if you want to work on that first assignment, or if you want to work on the second assignment. But I'll leave that for you. You guys have a great week. I'll be here Thursday if you have any questions. Give you the rest of the time to work on this.